So I think we could start, Michael. So just before I give the stage to the panelists, and the first panelist is going to introduce the rest of them as well. If you have any questions, let's keep them till the end of the session. There's a chat application there, and you can ask your question to the chat. I'm going to read them out, and I'm going to have one of the panelists answer your question. I hope it's going to work. So again, if you have any questions, keep them till the end, and then we'll open the chat for questions, for your questions and the answers by the panelists. So the next speaker is Michael. Michael, do you want to go ahead and introduce yourself, the panelists, and also show the agenda, and then start your presentation?
Yes. So this is Michael Malms. I'm working in the ETP4HPC office, and I'm glad to take you through an introduction today. I hope you see the screen. So we have an agenda. There are 3 pieces of it, or in it, 20 minutes about the general concept of the TransContinuum Initiative. And then we have 2 use cases, which are perfect examples for how this continuum is applied here. We have the first one from Dirk Hartman from Siemens. This is a real-time digital twin use case. And then we have the next one from Bauer from ECMWF. And this is about extremes prediction. You will ask maybe why digital twin use cases. I will explain this in my first part. And if you don't know what TransContinuum should mean, then this is not a problem. I will also explain how this whole initiative was set up a few months ago. So if you have any questions, and please use the chat, and we'll come back to your questions after the presentation. So let me just make sure this works. Okay, good. So TransContinuum, this is a word, this is not an official word. We created this as a brand name, basically. It has 2 pieces. Trans means across, and continuum, by continuum we mean the compute continuum or digital continuum. So the idea is just the opposite of siloed areas like HPC, cloud, big data, AI, and everything just by itself. We think there is a continuum, and you will see through the 2 use cases that how this continuum is supposed to work. And this initiative basically means that 8 organizations have joined last year together in this initiative to work together. And we have objectives, we have a scope, we had also a press release. We're now talking to the European Commission. This is all going on, and you will understand more in during my session here about this. So my part starts with what is the starting point for this initiative, then the basic concept, scope, objectives, and the ETP4HPC motivation, and then who are the partners and next actions. Also, you might, not sure, you might have seen a press release that we issued on December 11th. This press release made it into various streams, information streams, for instance, here inside HPC. And maybe you have seen this before. If not, you can certainly go back to that press release. So where did this whole thing start? The ETP4HPC has issued a so-called strategic research agenda last year, beginning of March. And in this initiative, or in this agenda, in this document, we talked about the fact that HPC is not only anymore a silo. So basically supercomputers hidden in some data centers that of course will continue to exist, but that's not the only way HPC is going to play in the future. There's this idea, and to be honest, HiPEAC was creating this idea, I think in the vision document in 2017, when HiPEAC introduced this idea of HPC in the loop. And you see here also the loop. So the idea is there are many disciplines that are interlinked between them. And HPC, cyber physical systems, smart sensors, Internet of Things, big data, and data analytics are all somehow connected by very dynamic and very complex workflows today. And in this SRA, we started to talk about the future initiative. We said we would like to not only talk about this here in this document, but see who is representing these different disciplines and what are the associations or projects to join. HiPEAC, by the way, is one of the partners here and has been joining as the first organization to support this idea. So during the first weeks of interlocks between the partners, we then said, okay, we have to beef this idea a little bit up. And it's not only about different disciplines that are connected in this kind of a loop. We also need to add a few more disciplines which are touching on all of them. For instance, mathematical models and algorithms. Really, if you start from the center here, you say, okay, data and compute platforms, this is the center of anything that is working in this IT infrastructure. Then you would say, okay, mathematical models and algorithms is the fifth thing you need around this. And then, and they have influence on all of these 6 different disciplines. And then you also, of course, artificial intelligence is going everywhere. You have then the 6 bullets that we talked about before, and then everything is protected by cybersecurity. So basically, we have these 8 disciplines that are all somehow intertwined, and now I'm just talking now about what in this is the ETP4HPC's idea. Why did we join? Then I'm going to show you the partners. So the ETP motivation in this is when you look to the future main areas of our involvement, you certainly, we have to continue in Europe on the road of exascale computing. That is the first disciplines, and depending on where you look on the globe, one geographical area might be sooner there than others. Certainly this is the priority number 1, to get to the next level of scalability called exascale. Then there is a renewed, or let's say an intensive also push on getting prepared for quantum for HPC. Certainly quantum computing is a very new discipline. And the question is, how much can HPC take advantage out of this new technology? And the idea is quantum computing, while there is still a lot of things to be done in order to make this usable. The first way this is going to work in the HPC arena is as dedicated accelerators. So preparing for this quantum-based acceleration is the next to do for us. And then, and this is now touching on this TransContinuum Initiative, we need to extend HPC for the future also by connecting it to the other disciplines. So extending our technical expertise through horizontal partnerships is a priority. And then doing this in a way that we have a balanced, well-synchronized approach by recommending R&D recommendations or R&D topics to funding agencies. So the major thing that the ETP4HPC is doing on the technical side is, of course, proposing R&D priorities for the future years. And doing this now in this TCI context means that we are not only proposing HPC-related research topics, but also topics that are interlinked and synchronized with other areas. And we're not only going to Euro HPC as one funding agency, but also to other funding agencies as well. And then one other proposal is to have a closer interlock with certain new European R&D programs like 5 missions, like Destination Earth, and I'm sure that Peter Bauer is going to talk about Destination Earth, and Gaia-X. So the TCI partners, this is the press release dated December 11th, and you see down here the 8 partners that have joined together. So this is, first of all, 5G IA, the 5G Infrastructure Association, then the association standing behind the Internet of Things called AIoTI, then the Big Data Value Association, BDVA, then CLAIRE as representing artificial intelligence. Cybersecurity is represented by ECSO, then the ETP4HPC, the area of mathematical models and algorithms is represented by EU Mass-In, and then HiPEAC, of course. So here on the right, you see the signatures of the heads and the chairs of these 8 organizations. And we do entertain pretty close links amongst ourselves. First of all, we have a core team set of meetings which is basically the steering element. So if there's anything to decide between the 8 organizations, then this is the forum to do this. We also do use case analysis, and the 2 use cases that you're going to see in a second are the first ones that we're analyzing to a pretty detailed level. Why we do this, I'll explain this in a second. We had the first kickoff on December 14th, and then we have quorum calls. So anybody who's interested in understanding what the future is all about here is welcome to join. The quorum calls are happening every 3 to 4 weeks. And we had in the last calls close to 40 participants. And we have, of course, now events and slots, not only today and during this HiPEAC Summit, but also during the Euro HPC Summit week coming up in March. We plan to have joint webinars. So the basic concept. So what is this all good for? And I briefly mentioned this already. So our idea is that we say, if you look to the use cases, then you will see that there are lots of challenges still that need to be solved and overcome in order to implement this technology. And these challenges are not coming in silos. They are coming in this kind of connected scheme of different elements. And I think there's nobody today around that is thinking horizontally, thinking out and proposing holistic research areas or research domains, for instance, to the European Commission, for instance, to Destination Earth, for instance, to Euro HPC, to other JUs. And this is our to-do. We are the body, or let's say the initiative, that looks out left and right and thinks holistically. And of course, engaging with European R&I funding agencies is, in that context, very important. We are now in the process of making our first interlocks with DG Connect. I have a chart on this coming up very soon. Generating and fostering this interdisciplinary work is important. So exchanging information about upcoming calls, about work programs, about options for getting engaged as an initiative is important. We also, of course, help each other in the forming and generating of our SRAs or SRIAs. And very important, we're going to interlock with the 5 Horizon Europe missions very soon to see how we can be helpful there. When I say helpful there, this means understanding what their requirements are in order to implement the underlying technology for these missions, for instance, beating cancer, CO2 reduction, smart cities, in order to go there and basically push the envelope over the next 7 years by each of these missions. You certainly are demanding advancements in the underlying infrastructure, and this is where I think we can become useful. If you are interested in having a little more in-depth insight into these 5 bullets, there is a vision document that we created together late last year, and you just contact us and we can send you a version of this text. So now we try to slowly make the bridge to the next 2 sessions. We said we would like to do a use case analysis of a specific type of use cases, and this is the set of digital twin use cases. Why digital twin? Because these are use cases that go from the assumption that you have a digital and a real incarnation of your technology. And the digital incarnation or model, in order to get there, you need, of course, computing, high performance computing. And in between the two, you have a lot of digital continuum technology. So these use cases are very widely spread. You have examples in the industry, mobility, environmental protection, energy, and you will see this in a second when we have the 2 sessions coming up. And digital twin use cases are very much in the center of the interest of the European Commission. Okay, next actions. I think I need to speed up a little bit. So this is this chart and one more. Getting with the European Commission to make ourselves known to them. We had our first step there. Then connecting to Horizon Europe missions, to big projects like Destination Earth is on our plate. We continue to have the use case analysis, and we're publishing white papers on these use cases. This here is our map of DG Connect, and you see the red circles. These are all the departments that we're about to contact or have contacted to basically let them know, here is this initiative, how can we interlock with you. And certainly we like to go up this org chart and up with the presentation to Roberto Viola. So this is it. I hope I'm in time. Martin, we can move.
Okay. So I need you, Michael, to unshare your screen. So
yes, I share this. Yes.
And Dirk is next. We can't hear you, Dirk, for some reason.
You able to hear me?
Yes, we can now. Yeah.
To
share
if
you want to share your screen now.
Screen.
Yes, it's coming up.
Okay, perfect.
Yeah. So I'm gonna hide my mug. Very good. Off you go. Thank you.
Good. So thank you very much for the introduction presentation, Michael. So this is to give you a little bit more detail and more flash behind some of the use cases we have in mind speaking about digital twins. In this case, or in this presentation, I will focus on what I call real-time performance digital twins. Let me jump over that first slide. That is a small explainer for all of you who would like to know a little bit more about digital twins, and is one you can find easily on YouTube. So let me try to explain in my words what is a digital twin in a nutshell. So first of all, I would like to stress that the digital twin is nothing really new, but it's rather the logical evolution next step when we speak about digitalization of design, engineering, simulations, and all those very classical fields where lots of the HPC community is coming from. Being myself a mathematician, I'm always inclined towards giving a short definition of the digital twin, though my feeling is that in the meantime, there are so many digital twins and digital twin definitions outside, so that I would rather call this a philosophy. And the philosophy behind the digital twin is that, their digital twin is a virtual representation of a physical object. And it really integrates all kinds of different data, whether it's models, sensor data generated or collected during operations, whether it's requirements documents, service reports, so any kind of digital information. And then it's not only collecting the digital information for the sake of collecting it, so it's not yet another database, but it always has a purpose and always should have a business-driven purpose. And if we go back to the NASA, who originally introduced the concept, the purpose of the digital twin, how they see it is to replace the real digital twins. They have every spaceship satellite they shoot into the space. And they go back to these real digital twins, to these real twins, to do troubleshooting, to do several considerations when it comes to service. And their key vision is to replace those physical twins with digital twins. So in their case, it's service, it's operation optimization. The goal, you can see here already, is always to reproduce the state and behavior of the real counterpart, the physical system, with the goal to predict and ultimately, of course, to optimize the performance. Though I'm coming from simulation or strong simulation background, obviously you can also do these days a lot of prediction with database methods, and I'll get to that in a minute. Looking a little bit what is out there in terms of definition, it's a very, very broad scope, and I would put here, or just selected here, the two extremes. On the one hand side, it's probably only digitizing and collecting, visualizing the information, all the way down to really predicting and optimizing behavior of a system by means of that digital twin. We'll get in a minute, 2 minutes to the use cases, and I hope that makes it much more obvious what the digital twin is about. So why are we speaking really about digital twins today? I mean, as we've seen, it's nothing new. So why are they really hot, and why is the time right now to look at digital twins? And the major reason, again, from a very, very personal perspective here, there's lots of other drivers, is fourfold. On the one hand side, the computational power we have today at our hands, I think is really the first time we can really try to address complex systems with all the different disciplines and domains simultaneously. So having this explosion of computational power, that's one key driver. Then at the same time, it's obviously not only the compute power, but it's also the algorithms running on that compute power. And I mean, there's various comparisons and studies, and if you look at those, you can actually see on the performance of the algorithms a similar growth, exponential growth, like Moore's law. So that would mean if you would take a 60-year-old computer and just take newer algorithms, you would also see the same exponential growth in terms of computational capability. So that's more the algorithm and computational capability. And then on the other hand, there's lots of things happening making the usage much easier. Because what we actually see today, in a particular industry, that many opportunities to use digital twins is kind of blocked, or big challenges are to get the required resources to realize digital twins, to realize the models, to set things up. And here, on the one hand side, novel human-computer interfaces are really being more and more adopted, and allow also for non-experts to at least easier interact with 3D or complex digital information on the one hand side. And on the other hand, semantic standards and knowledge graphs make it really much easier and more convenient also to find the relevant information, to transform the informations between the different data silos, and through this take out lots of manual effort to set up those digital twins. But then of course there's lots of many others, drivers outside, like the growing sensor data, the ease of communication using 5G, increased security. People are getting more and more open to share models, etc. So there's quite a number of drivers, and here I focused on the one, or the core 4 ones, which I'm mostly interacting with. What I would like to highlight in particular is really this interface, or the relation of, on the one side, simulation and machine learning. And this is really, from my point of view, 2 completely orthogonal approaches. While simulation very much leverages the knowledge and detailed knowledge we have about system, machine learning really scales with available data. And so that's why these axes are orthogonal. And also, if you look on the right-hand side, weaknesses and strengths, it's quite complementary. So that I truly believe that really this next generation of digital twins, it's really about trying to bring together those separate communities of machine learning and more the physics-based modeling community. And I think this is also nicely reflected in the TransContinuum Initiative in terms of partners driving this. And all this together is that really people on the industry side, as well as on the science side, get really excited about this digital twin approach that really will support. Now this is ASSESS is a community of analysis, simulation, systems engineering, software providers, and engineering service providers. And they really see here a key lever for improved decision making throughout the entire life cycle. And I'd like to stress here this throughout the entire life cycle. So not only in the design and engineering, where probably simulation was usually is based, but really also to leverage this knowledge across the complete life cycle. And again, similar statements you also find more on the scientific side in terms of that this really significantly will drive discovery of new fundamental natural laws, for example. So that's why I am, and many other peoples are very excited about digital twins. So now let's take a closer look really on a few use cases I brought you here where I have worked in the couple of months and years on. What am I speaking about when I speak about real-time performance twins? So to make it very black and white, I would split the life cycle into an offline phase and an online phase. In the offline phase, I would put everything what is classical design and engineering technology. So really building models, validating, optimizing models, and trying to iterate the design. And then the online digital twins is about taking this design or these simulation models, accelerate them so that they're capable to run in real time, and then run them in real time at the edge, on a control, somewhere in the cloud, so that they can really not only support decision-making on the engineering side, but also decision-making on the operation side. So for example, choosing different operation strategies, when to do service, etc. Ultimately to scale the performance of the operation. But then the other opportunity is obviously when you have models and you have data, you can combine the model and the data, and ultimately then also feed back that knowledge to the next generation of design. Also, what I like to stress here, coming from an industry background, obviously, if you do this offline digital twin in the design engineering, then that is something which scales, or the adoption scales with the number of engineers and experts out in the field. Whereas if you really have these simulation models running in parallel with the assets, then it scales really with the usage of the products and not with the number of experts in the design engineering departments. So now to the use cases. The first use case I'm going to present is about using digital twins to enable robots to do milling tasks. And what you see here in the background is a robot, a very classical robot, and those have been used for milling tasks since a long time, but only for very soft materials, so foams, woods, but never for metals. And the reason it's not used for metals is because during these milling, there are quite high process forces, and the process forces act on the robot, and that leads to a deflection of the robot. And typically that deflection for a typical milling task is about 1 to 2 millimeter. And obviously, if the part you're machining is 1 to 2 millimeter off, that's far out of scope of any industrial application. So what we've done here is realize such a real-time digital twin, run it in parallel to the operation, predict the deflection, and then counteracting that deflection. And by doing that, we could really reduce the errors made to 0.1, 0.2 millimeters. And that is on the scales, so that you can use robots to perform at least roughening tasks for milling. And there's quite a number of interesting applications, because obviously robots are much more flexible, much cheaper than classical machine tools. And the ultimate idea here is really use the digital twin, the digital information to compensate for the missing stiffness. Just to give you a feeling a little bit what is behind there from a technology point of view, on the one hand side, that is highly efficient geometric models to calculate the amount of material taken away. And here, it's not only about the efficient models, but also efficient or effective parallelization. Here we use GPUs so that we get in the required time to accurate predictions. And that's rather large scale processes, because on the geometric level, we need to go down to 0.01 millimeter. And the length scale of typical parts could be up to 2-3 meters actually. So really need to bridge those broad length scales. And then in the end, once we have an online prediction of the forces, that needs to be seamlessly integrated into the control process, so that it really can counteract the deflections of the robot. And the time scales we are speaking here about is hundreds up to thousands of hertz. So it means 1,000 calculations per second to compensate that deflection. That is the first use case. I'll jump here for the sake over the second use case, and rather look a little bit more on the third use cases I brought here. The use case here is about large drives. What you see on the picture is unfortunately not a large drive. So large drives really has the size of the room. So the demonstrator we built up here is using rather small electrical drives. And the key issue of those large drives is that they tend to heat up during the startup phase. And heating up means a couple of hundred all the way up to 1,000 degrees. And that is, of course, something you absolutely would like to prevent, because then it really leads to damage of the drive. The temperature occur at the rotor of the drive, and that is something we can for various reasons. So don't ask me, I'm not a motor expert, but you cannot put any sensors. So you have no clue what temperature is happening at the rotor, which in the end then leads to very conservative operation strategies. And the question was here, can we relax a little bit on the operation strategies? And those typical large drives are used in the oil and gas industry. And in the oil and gas industry, an hour more of availability is quickly a 6-point financial number, so 100 to 200,000 euros. And so it's highly attractive to trying to relax these strategies. And the key idea here is what we do. Again, we take this performance digital twin. So we take a digital twin running in parallel to the operations, and which can predict the temperature everywhere in the motor. Obviously, there needs to be some calibration and uncertainty quantification in place. So what would be the maximum temperatures, and can we calibrate them with a few sensor values we have on the hull, on the starter of the motor, and then predict it down what is happening at the rotor. And if we have a quite secure prediction, we can then relax the operation strategy and actually switch on the motor a little bit more early. A small disclaimer here, we always show this video, and it's very important, was very important to convince the stakeholders that we can predict the temperatures everywhere in the motor, though I would like to stress the fact that for this task, we only need the maximum temperature on the rotor. So all this complete visualization would not be necessary, but on the calculation side, the procedure is exactly the same, running it with the motor. The key ingredients here is the model order reduction. So speeding up by efficient pre-calculation of the simulations. So once we have the design models and engineering models, we take them, pre-calculate a lot of things so that then during the operations, we can scale up the speed by a factor 1,000 to 10,000 of the thermal simulations. Second point is really this continuous calibration. We have a few sensor values, and we use that to give it an uncertainty quantification or a reliability measure. And then what you see here in the demo is this immersed user experience that was very important to convince the stakeholders, but not really for the operations, as you see at the bottom. It really boils down also to quite nice business models where this can really be used. So that is a second use case, and for the sake of time, I would skip here over the fourth use case and rather take a little bit time to focus on the key challenges and performance digital twins. So I think still a big key challenge is what people these days are coining scientific machine learning. So to really integrate the machine learning, classical modeling, simulation, optimization technologies and integrating, I mean, beyond really just generating data with simulation and train with that neural network. And I believe that that's a key lever to then come also to real-time simulations. So how can we really efficiently come up with these real-time simulations? I mean, also these real-time thermal simulation models, it's probably nothing new. I mean, people have been using that, but to generate these things without or with only very, very little manual effort, that is key to really scale that up. Uncertainty quantification, of course, if you'd like to use that to guide operation strategies, then you would like to make it as certain as possible. Next generation compute architectures, you've seen GPUs was in two cases, or in one case, a key enabler. Also 5G, so I think really trying to think how we can work with next generation compute architectures, these tensor processing or neural processing units. How can we run classical algorithms on this? I think that's still lots of things to exploit in the future. Democratization, I think, a key issue we have today, that whenever we speak about all these complicated simulation methods, we always require highly trained experts to run these, but unfortunately the number of experts is limited. I mean, we just can't produce more experts from our universities, at least not in the near future. So we need to take these technologies and then put them onto a broader basis who are able to use that. Speaking about these operations, deployability to make this easier. We need new concepts, how to keep things synchronous. I mean, and then of course, if you change a part in the machine, you also would need to update the digital twin. And obviously all this comes also along with lots of security issues. Not only, I'd like to stress that not only of how to keeping the models safe, so that because obviously if you have a model, reverse engineering gets arbitrarily cheap. But also coming up probably with new security concepts when you have models. So there's also quite some thoughts around that. Again, put into this methodology, I don't know, Michael, if you would like to explain a little bit afterwards, the TransContinuum Initiative. So it's really trying to see along the different building blocks in this initiative, how do the challenges relate, what do we have to do? And then starting from this to really put down the specific roadmaps. And with this, I would like to close. As said, digital twins is not new. Early concepts have been around since a couple of years, so not named at that time digital twins, but really in terms of our capability, the age of digital twins is just to come. And I think right now we have a very, very great opportunity to shape that future. So thank you very much for your attention and obviously questions if there are any.
Thank you very much. So Dirk, I need you to undo your sharing the screen, if you don't mind, and the question will come at the end.
Okay.
Do that. So, grand. So Peter, you can now show your screen, hopefully. Bingo.
Okay. Very good.
And then you want to do it full view, yeah?
I do. So thank you very much for the opportunity. I hope you can see this in full screen.
Yeah, we can see it, yeah.
So this presentation is about an entirely different type of digital twin thinking, and this is about the Earth system. So obviously, the twin doesn't serve to design anything or engineer anything because we have the Earth system out there. It is really about monitoring the change that is happening and trying to influence and adapt to the changes that we can see and that we expect in the future. So it's about monitoring environmental change and predicting possible trajectories of that change in the future under climate change, with a particular focus on extremes prediction. And obviously, the digital TransContinuum has a big role to play there. And I'm going to try to show you how that works. Just one slide as a motivation related to extremes. This just came out a week ago or so, issued by the National Oceanic and Atmospheric Administration in the US, collecting the statistics of the billion-dollar weather and climate disasters related to extremes over the last 40 years. And if you look at these numbers, they're absolutely staggering. So over the 40 years, there was a total of over 285 such cases. So cases that caused damage and cost of over $1 billion. And the total amount of everything is close to $2 trillion. And of course, many lives were lost in the context of these things. And that kind of explains why we need much better capabilities to monitor and predict these events. In Europe, we have an activity that is called Green Deal, and I'm sure most of you have heard it. And in the context of Destination Earth, which is one of the key actions of the Green Deal under mobilizing research and fostering innovation, some of these aspects of extremes prediction and dealing with climate change responsibly in Europe to make sure that the socioeconomic implications are responsibly dealt with is featured. So Destination Earth will start in 2021 and aims to operationalize what's called digital twins for the Earth system by 2023, 2024. And it comes with its own funding and with its own governance, and it's supposed to last for the entire 7-year program of the Digital Europe program in Europe that is funding it. So the fortunate situation we're in is that we actually have a funded effort. It's institutionally funded, and now we're trying to define what digital twins mean under Destination Earth and how we're going to make them operate and function by the time we promised that operationalization. There have been a couple of very visible publications in that context that you may want to look at. One has been a Science article near the end of last year. Another one in the New Scientist and related to HPC, a publication in HPC Wire. They all deal with Destination Earth. They all deal with the digital twin capability in the context of the Earth system and the related Euro HPC or supercomputer infrastructures. And the main features that we're going for under Destination Earth are along 3 major breakthroughs. One is that we want to develop and deploy much more realistic models that are constrained by much more and better observational capabilities. So really, in the context of this hybrid extraction of information from both simulations and observations, just like any industrial digital twin. And that comes with an extreme scale computing and data handling footprint. We need to much more closely integrate the impact sectors. So these sectors that require actionable information and must make decisions regarding climate change related to, for example, how we deal with renewable energy in the future, the management of food and water resources, or finance and risk management. And the last is, and that is really at the heart of the TransContinuum, is the open and interactive access to data, software, and workflows. So if you think of that simulation and observation framework that I mentioned at the top here, that needs to be supported by interoperable software, open data, and as much as possible, allowing non-expert users from these sectors to actually intervene with that software and the workflows. At the beginning of the exercise, when we started planning for Destination Earth, we kind of had this vision here on the right-hand side, where you have everything that sits on the extreme scale capabilities, what we need in our specific domain to realize a digital twin when it comes to observations or simulations, with what at that time was called HPC in the loop and is now our loop of the TransContinuum. And the two together create, so domain specific and generic below create a digital twin. But as I said before, for us, it's really important that it interlinks with these impact sectors, because only then we can make sure that everything that we create in terms of data, computing, and infrastructures turns into value for our society. So our users are not engineers, our users are society in the end. So looking at specific elements of that loop or this TransContinuum, we can certainly say that there are emerging infrastructures in support of smart sensors networks. We don't have much experience with this in our present operational systems, the way we work with Earth system models and observations today. But there's certainly opportunities using data from mobile phones, certainly in areas where mobile phones are the only communication resource that's available, like in the tropics, where we have very few other observations actually. So there, the resource of mobile phones is incredibly valuable for us. The other point is probably urban areas with the high density. And if you want to go into smart cities and urban modeling as a subset of Earth system modeling, then this kind of resource is incredibly important. But similar deployments of such sensors in wind farms, thinking of smart farming, is certainly important. We have some of these resources already in terms of air quality. Most of these are publicly funded, and we need to make sure that we also get access to those that are provided and deployed by private groups. IoT is interesting for us as well, certainly in terms of the way this information is relayed through the IoT, so the dissemination of such information, and how these devices are integrated in a prediction and observation workflow. Some of this already exists. There's very large companies like IBM, but there's others. The part of their business model in weather and climate prediction is actually that they have access and unique access to IoT devices and their own privately owned networks of observations, and that they combine that with their own simulation capabilities for very specific prediction questions, mostly in the short term and highly personalized, which is a deviation from what we do in the public services, but that tells you a very strong integration already of these capabilities in future prediction systems. Private now, probably public in the future. We certainly have a big data problem. This is an area we're quite experienced with, which doesn't mean that we have solved all the challenges. On the left-hand side, you see the accumulated archive growth in common meteorological systems, and you see that this grows at least linearly, if not exponentially in cases. It's the combined data from observational networks and simulations, and simulations usually outpace the observational data in terms of volume and diversity. On the right-hand side, you see just at our center what we expect in terms of daily production rates, moving from today, where we have roughly a bit more than a petabyte per week, to something like a petabyte per day in only a few years. And if we think and extrapolate that into the future, we expect a proper extremes digital twin with very high resolution models and many more observations than available today to reach 10 petabytes per day. And that's not only an engineering problem in terms of how you handle these amounts of data, but how you then, extract the important information from such data and relay that to the impact sectors like food, energy, and water that I mentioned before. I want to make sure that you realize our difficulties in supporting our digital twins with algorithms. Our algorithmic framework is quite diverse. Opposite to engineering applications like for engine optimization or something like that, we have really a multi-scale, multi-physics problem, because as you just have to look outside and you see that you have large scale dynamics in the atmosphere, the big atmospheric waves, for example, and then you have very small scale effects like turbulence, like evaporation, like radiation, cloud physics, for example. So we have quite a range of orders of magnitude of scales these processes interact on, and that we need to reflect in our systems. And that makes our Earth system simulation side of things quite difficult in terms of representation of realistic Earth system physics in that twin. And it also makes it very inefficient on HPC systems. So what we achieve right now in our systems, regardless of the choice of algorithms in the end, is 5% or a bit better in terms of sustained performance. That's something we're working very hard at. And for us, therefore, algorithm design that follows digital technology constraints is really important. So I think there are solutions and options for us where we need to probably make our algorithms slightly cheaper, maybe at the expense of some accuracy, if it comes with a significant efficiency gain. So this is something where at the center of the TransContinuum figure, this ring on algorithms and numerical methods is highly relevant for us to work on. So that's a central part of our concern. I mentioned HPC already. I mentioned the 5% sustained efficiency that we right now achieve. If we extrapolate our HPC needs to the future in terms of what kind of Earth system digital twin we would like to operate, we conclude that probably present day systems, so simulations run on present day infrastructures, are about 100 times too slow. Which means that we not only need bigger computers, but much more efficient computers. So invest in the technical digital technologies that allow us to run systems or simulation systems more efficiently, and back to the algorithms, maybe pay a price at accuracy for the gain of efficiency. So it's really a multi-body problem, and we need to look at all the individual elements in the circle to achieve this factor of 100 of acceleration and performance increase. We have ideas for how to do that. This is a figure that will be published at the end of February in the new Nature Computational Science journal that just started in January this year to publish. So we have ideas about how to set up the workflows, numerical methods, the programming approach, making the best of the available technologies in a holistic system. But we haven't done it yet in practice. We've only solved parts of that in practice and demonstrated parts of this. So bringing this story together across all the elements of HPC big data and the other elements in the TransContinuum that feed into it is right now our agenda for the next coming years. Machine learning, I should mention. Machine learning for us has a lot of potential in many different areas. It's not only extracting information from data. I mentioned the 10 petabytes per day, from which we need to extract information that is relevant, actually. So this has to happen fast. So there's a couple of aspects that we're currently focusing on. One is simply acceleration in computing. So, replace very expensive model components or processing components through surrogate systems driven by machine learning methods. The compression of data I mentioned, the extraction of information I mentioned as well. And then certainly at that front end where scientific data needs to be translated into impact sectors, so energy, food, water related information is very important, and there machine learning is going to play an important role. There's certain issues related to that you're all familiar with, at least those of you who are looking to machine learning and AI, and of course many pitfalls, and we have to make sure that we take care of those as well. So in the end, it's physical systems, the Earth system as a whole, that we influence as humans through, the emission of greenhouse gases, but other things as well. So there's a holistic global problem, but underneath sit many specialized problems. And I mentioned smart cities or smart farming already before. So you have to think of this as a hierarchy of digital twins, actually, where you have the big system driving everything that comes below, and where you then have specialized or specialist options that allow you to run these systems more efficiently and with more reliable forcing from the big system, when it comes to how climate change will exactly influence smart farming in the Mediterranean versus the central US or somewhere else, for example. And then at the last, nearly at the end of the presentation, the same setup that was shown before by Dirk, kind of a top-level judgment of where we are in terms of exploiting the individual components of that loop. For some things, we have more experience than for others. Extreme scale computing, I've mentioned. Machine learning, we have a bit. Extreme scale data and observational data access, which doesn't mean that we have solved all the issues. As I said, we have experience, decade-long experience with extreme scale computing, and still only 5% sustained. So there's a lot to do. But there's other areas, certainly in the digital twin area up here. Smart sensors is something else to mention, where we're just starting actually to look into what new technologies have to offer. But I think I can have convinced you that all these elements are highly relevant. You can do this mapping exercise the other way around. So this is, with a loop at its center. This is with our workflow at its center, starting left with a collection of observations that we collect, put together, where we bring together the Earth system model with the observations to have the best possible view of what the state of the Earth system looks like today, and where we then produce predictions that are then disseminated, archived, and transmitted to these impact sectors, for example. So this is our linear workflow. And if you then look at the individual locations where the individual components of the TransContinuum are most important, you see edge is highly relevant, where we collect observations, for example, HPC at the center, where the heavy engineering and calculation and data management lies, and then everything else that sits on the front end towards the users. A lot of possible federated cloud operation. And there's storage elements, there's IoT and other options. And machine learning, as I said earlier, cuts across everything for different parts of that workflow with different functions. So in the end, what we want to do is we create digital twin engines that are fairly generic actually for our applications. And you could think of this as a big Earth system simulation model supported by observations. Ideally, you do this in a simple generic framework in that software view I've shown you from that publication earlier. With this digital twin engine, you would support this hierarchy of digital twins for global concerns, for farming concerns, or something else. So you would use the same engine in different types of cars in this car analogy. And then you would serve with those digital twins just quite a large number of use cases actually. So you use your cars for different purposes, like that single van, then for either traveling, go to work, or go shopping. So you diversify from left to right, ideally relying on very generic infrastructures to begin with. And this is what Destination Earth is about. And with this, I think I should stop and we can all take questions. Thank you.
Thank you very much, Peter. So could you release the screen? You have, very good. So I'm going to show mine. So if you do have any questions, could you maybe try to raise your hand through this application, and then, hold on a second. Yeah, so if you raise your hand, I can let you speak because there's not too many of us, so I can activate your audio. Otherwise, if you could use the chat to write a question, I will read it out. Okay, I don't see any questions. Let's wait a minute. So do you have any questions? Okay, I don't think there's questions. So in this case, I would like to thank you very much. Many thanks to our panelists for the presentations, and many thanks to the participants for taking part in this session. So I hope to hear from you soon. There is a series of webinars the ETP4HPC organizes now and then. So if you want to be part of that, watch our website. And with this, I'd like to finish this presentation. Thank you very much.
Thank you very much.
Thank you.